Okay, thank you very much for the invitation, and I'm really glad to be here, even if it's remotely, because I don't really see all of you very well, but I hope we can still have very fruitful interactions. And I'm really happy that I can share some of my recent work around lifelong learning. And during this presentation, I will try to explain why I think this direction of research is important, and I'll cover several of our research projects on that topic. Okay. I can't go to the next. Yes. So let's first start with some context. And let's start with a typical computer vision task, image classification. And let's in particular start with one of the favorite tasks of computer vision researchers, which I think is cat classification, let's face it. So let's assume that you would like to build an algorithm that is capable of predicting, when presented with an image, if it contains a cat or not. So what do you do for this? Well, typically you need images of what cats look like, which is surprisingly diverse. Optionally, you can have images of what cats shouldn't look like. Then you take your favorite architecture. This can be a convolutional neural network or transformers. You can take your favorite classification laws and optimization algorithm. And like this, you can train a model which, provided with a new image that it has never seen before, can predict if it contains a cat or not. And this simple recipe that I described is very powerful and works extremely well. And this is really what allowed us to build very strong classifiers, able to differentiate thousands of classes. And if we summarize the ingredients of this success, first, you need very large and fully annotated data sets, such as the ImageNet dataset that you all know. You need very deep neural network models with many, many parameters to train. And then you throw lots of compute at your problem. And just like that, you have very powerful models that classify thousands of classes. But now let's assume that you would like to use this recipe on a larger collection of tasks, just not one task, but many. If you think about it, dealing with each new problem from scratch sounds like a giant waste of time, of memory, and of resources. And that's why we're going to focus on lifelong learning, where you know beforehand that instead of solving a single task in isolation, you're going to solve many tasks. And you would hope that learning for one task should help learning for another. And in some cases, the learning sequences of the tasks can be as long and as complex as can be. So this is the kind of problems that we're going to look at today. And we're going to look at a number of these sub-problems to make progress on lifelong learning. So let's only consider two tasks for now. Let's consider a task A and then a task B. Immediately, there are two research questions that arise. The first one is, how should we train on task A? So your training is going to be as helpful as possible on this task B that comes next. The second question you have is, once you've done this training on task A, what is the best way you can adapt to task B? And keeping these two questions in mind, we're going to go even one step further, and we're going to consider that task A is just a pretext task. It's just a pretext to build a representation that is by design going to transfer very well to a task B that is still unknown. So that's the first problem we're going to look at into more detail, how to train transferable visual representations to a task that is still unknown, right? And I'm sure you all know that people have very quickly found out that models pre-trained on ImageNet, they were actually extremely useful starting points if you wanted to tackle other computer vision tasks with fewer training examples. For example, another classification task or object detection, instance segmentation, or even image retrieval. So if you think about it, fully supervised classification on ImageNet can be seen as a proxy task to train strong visual representations. Yet, assuming that you have a fully annotated ImageNet size training set that is readily available for your domain of interest, that's quite a strong assumption, right? So it would be interesting to be able to reduce the annotation cost that is associated to the proxy task that is used to build transferable visual representations. And that's what I'm going to cover in the first part of this talk. We're going to look at different ways to reduce the annotation cost when pre-training a model that is going to produce visual representations useful for something else. And I'm going to cover one method based on self-supervised learning and one method based on weakly supervised learning. So the first piece of work that I'm going to present today, we've presented it at the NeurLibs conference 2 years ago on a paper entitled Hard-Negative Mixing for Contrastive Learning. Remember, the goal is to train transferable visual representations. And the standard way to do this, as we just recalled a few slides ago, it is to use fully supervised classification on ImageNet. But this requires each image to be annotated with one label among 1,000. And these fine-grained annotations, they really require expert knowledge, right? Because not everyone can get the category of a specific mushroom or bird species right. So is there a way we can train visual representations with images only? So absolutely no annotation is required. And this is exactly what self-supervised learning is going to offer us. So I know there are several ways people define self-supervised learning, but if I had to define it in a sentence, I would say they are unsupervised approaches which borrow from the supervised techniques, except that the labels, they do not come from human annotators, but the labels, they're fabricated from the data itself. So let me give you a few examples. One of the early approaches that is based on such a proxy task took the proxy task of context prediction. So given a patch, extract it from an image, such as this cat face patch that you see. And let's take a second patch, extract it in surrounding. Then the model is asked to predict the relative position of the second patch with respect to the first one. So where is the second patch coming from? And you have a number of options that are the different little squares that are shown here. And as you can see, this is a supervised classification task because you have 8 labels. But the ground truth, this is not based on human annotation. This has been automatically generated from the data. And by training a classifier to get this task right, over thousands of patches on thousands of images, you can build a model that leads to very strong visual representations. It's been observed already back in the day, back in 2015. Let's take a second more recent example. This is quite intriguing because of the simplicity. It's a ROTNet model, which is simply trained by learning to predict the correct orientation among 4 possible options. And by training this for all the images of the ImageNet dataset without the labels, just by using the label being the correct orientation, just by training for this, you have a model that leads to very strong visual representations. And there's, of course, a lot more methods. Many methods have been proposed, and there's an excellent tutorial that you can find, for which you can find the slides online by Andrew Zisserman. So those were some of the early approaches for self-supervised learning, and many other pretext tasks have been proposed since then, as I mentioned. But among them, those based on contrastive learning have been quite popular in computer vision. So there's all of them slightly different, but most of them are based on the same kind of recipe. You take an image, you build two different transformations of that image, like this, and then you learn an embedding function that encourages the embedding of these two transform versions of the same image to be close to each other in the representation space and further apart from the embedding of a negative image. Ideally, any negative image. So in this case, the proxy task for learning a representation that we consider is instance discrimination. And here my negative example is a dog, but remember you have no label whatsoever. So a different cat would be also a different instance, so it would be considered as a negative because we have no notion of class. We just have the notion, are these two images produced by the same original image and differ only by a transformation? And this is a leading intuition behind the popular MOCO or SimClear approaches. And a co-observation that we've made while working on these approaches is that making the proxy task more difficult tend to lead to visual representations that are going to generalize better. And this is exactly what we want to do, right? Generalize to a new task that is still unknown. So how can you make the task harder? One thing you can do is to create better positive pairs, which means more challenging positive pairs by handcrafting the set of data augmentation. And you can see some of the transformation that have been proposed by the SimClear approach. Another thing you can do is to create better negative pairs, so more challenging negative pairs. And how do you build more negative that are challenging? Well, that's not obvious. So the typical way to do that is just by considering more negatives. And SimClear is doing that by increasing the batch size, and MOCO is doing that by using a memory bank. But what we observed while working with these models for a while is that after a few epochs of training, the vast majority of negatives are easy, which means that they do not contribute to the loss anymore. But a few of the negatives still exist that are challenging and bring a loss. So what we propose to do is to rely on those and to mix the hardest negatives for each query and to synthesize on the fly directly in the feature space additional hard negatives, either by mixing two negative samples or by mixing the query with a negative. And because everything is happening directly in the feature space, you don't need to re-extract descriptors for the image or applying new transformation or anything. So this is a very lightweight process. This can be done very easily inside your training algorithm. So we've called this technique mixing of contrastive hard negative, or MOCHI in short. And without going into the details, what we observed while playing with this method is that indeed MOCHI is making the proxy task more difficult. MOCHI better uses the embedding space, and MOCHI tends to transfer better than, and at least train faster than MOCO. So that's it for this. I don't know how you want to proceed, and if you want me to go through the entire presentation and leave the question at the end, or if you want to make something more interactive, that's also totally okay for me. So I don't know what you guys prefer. I don't know if there are questions so far, or if I should move on. Okay, I'll move on then, but feel free to interrupt me. So that for a first approach, whose goal was to reduce the annotation cost, let's look at a weekly supervised learning one. And this is a piece of work that we've presented at ECCV 2 years ago, where we focused on learning visual representations with captions. So as we said, when category labels are available, very powerful model can be built. But these require fine-grained annotations, which in turn require expert knowledge. At the very end of the spectrum, we've discussed self-supervised learning approaches. They were great, of course, but they either use large datasets, such as ImageNet, or even bigger and less curated datasets. So as a consequence, these approaches, they can be computationally demanding. In this particular work, we're looking for an alternative approach, which uses captions as a source of supervision and which would require fewer images. And we're looking at a way to train visual representations from scratch using a medium-sized set of caption images. And producing such captions, if you think about it, this doesn't require any expert knowledge. And sometimes captions can be collected automatically. That's why I'm going to treat them as weak annotations. So our work draws inspiration from the recent advances in natural language processing. You may be familiar with the masked language modeling task, where a token is randomly masked in a sentence, and the goal is to predict it by relying on the rest of the sentence. And solving for this proxy task leads to very strong language models, as BERT has shown, but also many other language models since then. In our case, we start from an image caption pair. So first, we mask a token in the caption. Then we try to retrieve the masked token using the remainder of the caption and the image. In this particular example on this slide, we would like the model to leverage the visual representation to predict the word umbrella. And once we've defined the proxy task to solve, we need to propose a multi-model architecture to tackle it. So such a model would require a visual representation. This is trained from scratch. This is what we're really interested in, right? We want to build visual representations. The rest is just a pretext. We need a textual representation. So here we assume it's provided, for instance, following the approach described in the previous slide. And then we need a few auxiliary modules that combine these two representations, the visual one and textual one, in order to perform the prediction task, predicting the mask token. And we call this proxy task image condition mask language modeling. And after the training, the only thing we keep is the visual representation, as I mentioned. Instead of showing you quantitative results, I'd rather show you qualitative results, where here you have visual attention maps that are produced by our model for a given image caption pair as we mask different tokens. So we see that the model can attend to different image regions depending on the mask token. And experimentally, we observed that this model that we proposed produce representations that tend to transfer as well as the one produced by self-supervised learning models, at least the one that were available at the time of the work, using 10 times fewer images. So this work has already a couple of years old. So what I would like to do is to take a couple of minutes to position this work with respect to other attempts at learning visual representations by leveraging text. Because of course there were many proposed before and after ours. So I like to position it properly. And this list is not going to be exhaustive, but this is to give you an overview. The first attempt that I'm aware of dates back to 2007, where Ariana Poitoni and her colleagues have looked at this task by creating and solving auxiliary prediction tasks using some images and their associated captions. 10 years later, this task has been revisited by two notable contributions. In the first one, label sets are constructed out of caption n-grams, and CNNs are trained to predict those labels. And in the second piece of work, topic models are extracted from Wikipedia pages, and CNNs are again trained to embed images in this topic space. Almost concurrent to our work, the VRTech approach was presented at CVPR 21 and uses the same data and the same proxy task as the approach. So really, these two pieces of work share many, many different things. So I encourage you to look at them, their work as well if you find ours interesting. And since then, many other approaches have pushed the idea of learning together with image and text. And maybe CLIP is the most famous of them that really pushed this intuition to massive scale by learning with hundreds of millions of image caption pairs. So now that we've seen different ways to build visual representations, I would like to briefly discuss a study we've conducted, which compares the properties of visual features in a way that is as fair as possible. And this is a piece of work that we've presented at ICCV last year. So again, we assume that there's a proxy task that is used to train a model. For instance, our proxy task can be fully supervised classification on ImageNet and its labels. Or maybe our proxy task is something less annotation hungry, like the two alternatives that we've seen previously. And we would like to evaluate the visual representations that have been produced by this proxy task. The problem here is that we don't know in advance which task the visual representation is going to be applied to. Remember, that was the initial motivation. So we would like this visual representation to generalize as well as possible. So how do we do that? Well, the way that is typically approached in papers is simply to evaluate the representations on a set of target tasks and data sets that is as large and as diverse as possible. And this gives already a very good first intuition on the generalization capability of the visual representations. But what about something slightly more principled? What can we do? So for our study, we focused on a single aspect of generalization. We focused on the generalization to new concepts. So we've been looking at the question, when training a model on a set of seen concepts, how well does this model generalize to new and seen concepts? So looking at this example, does learning about cats help us learn faster about caticorns, a category for which we have very few training images and very rarely photographs, I would argue. So how do we evaluate that in a principled way? Well, we need a dedicated benchmark. And this is our contribution in this work, a benchmark fully dedicated to the principled evaluation of concept generalization. That's why we call our benchmark COG. And to build such a benchmark, first, we need to define a way to compute the semantic similarity between concepts. The intuition behind is that tiger cats and European cats are more related to, say, tiger cats and cabbage worm, right? So for this, we decided to rely on the lean similarity that is computed on the WordNet graph, an ontology handcrafted by linguists. And with this similarity that produces semantic distance, we can rank categories from the most similar to the least similar semantically to a starting category. Now, the benchmark we propose is based on the exact same idea, except that we extend the measure to compute the semantic distance between sets of concepts. So remember, we want to evaluate concept generalization. So if we want the benchmark to truly evaluate concept generalization and nothing else, only the concepts should vary. The rest shouldn't vary, not the data distribution, and we should have as little variation as possible. So for this, we decided to build a benchmark on the full image data set. So not the small ImageNet with only 1,000 categories that people use for the challenge, right? The full ImageNet with the close to 20,000 categories. Then we define a set of seen categories, which are the only ones that the model are exposed to when learning visual representations. For this, we use the 1,000 categories of the ImageNet challenge. And that's convenient because many methods use this set of seen categories anyway to train their visual representations. So this allows to evaluate directly many models that are available out there. Then we build 5 sets of 1,000 categories, which are increasingly distant from 1,000 categories of the ImageNet challenge. So the idea is that dealing with these different levels should require more and more generalization capabilities. This gives us a full benchmark composed of a well-defined training set that is composed of images from seen categories that are the only one the model are allowed to be exposed to train the visual representations, and 5 test sets of increasing difficulty, which we call generalization levels. And that's the benchmark we've proposed. I will not go into the details of the full study we conducted with the benchmark, but we used it to compare a number of approaches, all these approaches that were proposed to learn visual representations. So we have a number of supervised approaches, weakly supervised approaches, and unsupervised ones. And we've made a number of interesting observations. I will not discuss all of them, but at least there's one that is very relevant for today's discussion. We've observed that the recent self-supervised learning approaches, they generalize very well to unseen concepts, even better than their supervised counterparts. And strongly related to this observation, I'd like to mention in very few words, a very recent follow-up work where we try to understand why labels, instead of helping, we're actually hurting the generalization capabilities of models. So we've evaluated a number of models that were available out there on 2 dimensions, on, first of all, their ImageNet results, because all of them, or most of them at least, are trained on ImageNet. But we also evaluated how they perform in terms of generalization to the COG benchmark that I just presented, and also generalization to a few other transfer data sets that people typically use to evaluate transfer. And based on this study, we've built a supervised approach able to create visual representations that are still very strong on ImageNet, but also generalize at least as well as self-supervised approaches to this COG benchmark and other datasets. We've named our approach T-Rex, and without going too much into details, key to the success of our approach are 2 components: heavy data augmentation based on multi-crops, something very similar to the data augmentation approach that has been implemented in Dino, one of the leading self-supervised learning approach. And the second component that is crucial to the success of T-Rex is an expandable projector head that is used when training for ImageNet, but that is discarded afterwards. And we've singled out 2 such strong models, T-Rex and T-Rex stars, which are respectively best at transfer and on ImageNet. So those models are available, and if you like, you can use them as starting point for tackling other tasks. So this brings me to the end of this first part, where we've seen 2 different ways to define a proxy task for learning visual representations. And these 2 ways, they require fewer annotations than the standard pre-training that is usually done in ImageNet and its tables. We've also seen how to evaluate how this representation generalize to new concepts in a principled way. And for the second part of the presentation, I'd like to go back to our initial motivation of lifelong learning, where instead of considering a sequence of tasks, we are going to consider a sequence of domain. So we assume that this task stays the same, but the domain varies. So this is continual domain adaptation. And the model should be able to adapt as new data distribution are encountered. So we can assume, for instance, that we've trained a model for clad classification, still our favorite task, with natural images. And this CAD classifier, we would like to adapt it to deal with paintings. And after a while, we get new data to adapt it to pixel art, maybe. And it's typically easy to perform domain adaptation in such a supervised setting. We know how to do that very well. But there's a downside when adapting the model, right? Because when adapting the final model, the one that has gone through the 3 training phases, the initial one and the 2 fine-tuning, when applying this final model back to the domains previously encountered, it turns out that it has almost forgotten what it was initially trained for. And this is a problem that is well known in the community as the catastrophic forgetting issue. So we're going to look at how to mitigate catastrophic forgetting issue in continual domain adaptation. And we've made a couple of contributions to tackle this problem. And I'll define more precisely the task we're going to look at in the second part. So you may be familiar with the unsupervised domain adaptation problem. There you have access to a large annotated set of data from the source distribution. And we would like to adapt a model trained on this data to a target set from a different distribution for which only unlabeled data is available. This is what people typically refer to as unsupervised domain adaptation. In this presentation, we will cover 2 other tasks. The first one, incremental domain adaptation. So here we adapt not only once, but we adapt multiple times. And we're going to look at online unsupervised domain adaptation, where the adaptation is done online for a target distribution that continuously varies. The 2 next papers will cover these 2 scenarios. So the first contribution, this is something we've presented at CVPR last year. And let's take the example of a self-driving car here. Here, we assume this self-driving car is equipped with a visual system that has been trained for a particular environment. And we would like to update this visual system as training data for new domains is provided. Maybe we encounter images from as a place where there's a lot of snow, and then we acquire new images where fog is present, and finally we have sunset images. The problem is that if we update the visual model without any precaution, as the model gets updated, it will likely forget the previously learned patterns. And this is what I mentioned as the catastrophic forgetting issue. We would like to mitigate such issue. A nice solution is simply to keep in memory all encountered training examples and retrain the model from scratch with all the data available every time. And this works extremely well if you can afford it, but it's obviously intractable for practical applications. Of course, it costs a lot of time, of memory, and resources to do this retraining. And on top of this, it's not always possible to store previous data, in particular for privacy reasons. So in our work, we focus on a method that doesn't store any sample for retraining. What can you do if you cannot store any sample? Well, let's assume that we will have layer to adapt to a future domain that is still unknown without forgetting too much. But we don't know anything about that domain. One thing you can do is to heavily randomize the visual appearance of the current domain samples. Intuitively, this increases the model's comfort zone and eases the process of adapting to the different domains. And in turn, this results in models that forget less. But we can also leverage these informations in a more principled way. We're going to call metadomains each set of samples that we obtain for a given transformation. Then during training, we train for three things. First and foremost, we train for the current task. So we update the model according to this training data we just got in a very standard way. Also, we can train in order to adapt better. For this, we decided to follow the meta-learning approach as described in the mammal paper of Chelsea Finn and her colleagues. Intuitively, this trains the model parameters such that a small number of gradient updates will lead to fast learning on a new task. Finally, and maybe more importantly to the topic of the task we're looking at right now, part of our loss tries to mitigate forgetting. So again, we follow a meta-learning view, and we run a single gradient step on each metadomain. And the core idea is to look at the weight configuration after these potential updates on these metadomains that are artificial, and consider the loss associated with the primary domain after those adaptations. So minimizing these losses will enforce the model to be less prone to catastrophic forgetting. Everything happens during training. So the technique I just described can be deployed without changing anything about the existing pipeline. You can keep your favorite architecture. You don't have to change the architecture. You don't store samples. You don't store extra parameters. So it's transparent. And also, it can be applied at every training step of the sequence, every time a new domain is encountered. So to conclude this part and looking at the lessons that we've learned, we've seen that domain randomization is a surprisingly strong baseline. I didn't show any experimental results, but like in the paper, we've thoroughly evaluated this. But we've also seen that domain randomization can be used to create metadomains, and that this results in a meta-learning approach that can be used for both faster adaptation and to reduce forgetting. Finally, for this presentation, I'd like to move to a recent piece of work that was presented 2 months ago at CVPR. And in this work, we consider a scenario that is even more realistic because samples, they do not come as batches, but they arrive sequentially, one by one, as the environment continuously changes. And our goal here is to adapt to sequences of samples that are temporally correlated and unlabeled. So each sample from the sequence triggers an individual adaptation problem. And the question we're trying to answer here is, how should we perform adaptation in that case? If you look at all existing benchmark for this continual domain adaptation a problem for semantic segmentation, they assume access to a label validation set. And this is an assumption that is not valid for many realistic scenarios, including ours. For this work, we've considered the task of semantic segmentation, and our problem is at the intersection of domain adaptation, online learning, and semantic segmentation. So we are more precisely looking at the problem of online adaptation for semantic segmentation. To tackle this task, we had to develop a proper benchmark to make sure that we have no access to any validation data when we deploy the model. So this benchmark is composed of 3 steps. First, we train a segmentation model in an absolute regular way, offline, looking at the data as often as you need in whatever order you need. And this produces the initial model that will be used later. Then the model is used to initialize the model of the next step. In this next step, the model gets continuously adapted as the new samples are required. Adaptation methods, as you can guess, depend on many hyperparameters, many design choices. So those choices are validated on a dedicated validation step. This allows us to choose the best flavor of each approach. And only this single best model according to validation is deployed on the test set. This way, models can't cheat and can't validate their parameters on samples from the test distribution. Instead, the test distribution remains unknown, which is absolutely required for proper evaluation. And this is our OASIS benchmark that we've recently made public. We use the benchmark to compare several approaches for adaptation. So we considered, as in the previous paper, domain randomization. Again, domain randomization means heavily randomizing the appearance of the training samples. And this indeed works very well because it reduces the chance of the test samples to be perceived as out of distribution. Next, we've considered self-training using pseudo-labels. In practice, this means that you trust some of your model's predictions, you use them as ground truths to update your model, and you repeat this several times. Also, the adaptation of batch normalization statistics. This is known in the standard domain adaptation literature, and this improves model performance at test time. So here we follow the same idea, and similarly, at every new sample that is added, we adapt the rescaling parameters of batch normalization. And we've observed this strategy to generally help. Yet the main problem with all the solutions, all 3 of them, is that after a while, we witness catastrophic forgetting. So if you remember what we're doing, we are learning to adapt in an unsupervised way. And it's not really trivial how one can prevent the model from drifting away and from starting to forget classes. What we observed in practical terms is that rare classes, they tend to disappear and they leave space for the more frequent ones. And this is not a behavior that we want for continual adaptation. So there have been some countermeasures, and among them, I can mention naive learning. So here, instead of doing continual learning, at each frame, we restart from the original model. Something we can do is to use a memory bank where we keep original training samples to the model, and we use these training samples that we've stored from time to time for retraining. Of course, if that's an option to store some of the training samples. And we've also looked into research strategies. So these strategies, they store and keep the original model as a checkpoint. And when some threshold is met of forgetting, we reset the model to this checkpoint that contains the original model. And I agree that they sound pretty naive, but these research strategies, they tend to work pretty well in practice. Here is a video that shows how without adaptation, the model has issues dealing with objects that it knows, but when they're observed in a different context. For example, here on a totally different time of the day, we have a very different light. If we apply continuous adaptation, we see that results are improved for more frequent classes at least. But we see that results decrease for the rare classes. And actually, some classes are completely forgotten and never predicted ever again. And finally, we see on the right that our sample reset strategy, it offers a reasonable compromise between the two extremes. So to conclude, we've seen that realistic systems can be deployed in the real world when you face a distribution that consistently shifts. Our benchmark reflects these challenges. We've seen that domain normalization build models that are resilient to domain shift. And we've seen that a naive adaptation frame by frame lead to catastrophic forgetting. So you need to do something to prevent that. A research strategy at least safeguards that no class is totally forgotten. So now I'm reaching the end of the presentation. I've covered quite different research questions, quite a few experimental protocols. We've seen many tasks, we've seen many domains, but all these questions we've looked at are all related to lifelong learning. And if I had to bring together, all these pieces of work in order to drive the take-home message, I'd say that we have progressed on several research questions. So first, the research question of how should we pre-train visual representations? We've seen that self-supervised learning is a great tool because such methods do not require any labels. And many pretext tasks exist. And in particular, invariance to data augmentation is one of the most standard one. Typically, they generalize great, especially to unseen categories, as we've seen today with one of the benchmarks that I showed. But they tend to generalize also very well to new tasks and new domains, and has been shown not today, but in concurrent work. We've seen that text is a great source of supervision. And we've seen in low data regime today, but large models that are sometimes called foundation models like CLIP, they've already significantly impacted the field. So multimodality is probably going to be central to many state-of-the-art systems in the future. In a second research question, that is, how should we pre-train visual representations so they transfer better? We've seen multiple evidences that making the proxy task more difficult leads to better generalization. We've seen how crucial data augmentation is to self-supervised learning, but we've also seen how domain randomization helps for continual learning and for online learning. We've seen how harder negative samples help in the case of the contrastive loss. We've also seen that meta-learning can be used to facilitate transfer, so that's also a promising direction. And finally, if we look at this question, how to mitigate catastrophic forgetting when we transfer, especially when we have multiple transfer steps, we've seen that in general, stronger pre-trained models tend to forget less. And intuitively, I think this is because the model are already pretty good, so they generalize well. And this means that they also require fewer training steps to adapt. So I think they're less likely to forget. One way to also forget less is by imposing the training set to favor solution for which adaptation to a new task is likely to leave the initial task unaltered. That's something that we've tackled using meta-learning. But there's other approaches that could probably be used to have this similar property of not affecting too much the initial task. And last but not least, we should put in place systems that detect catastrophic forgetting. And this is the only way we can start having adaptive system being deployed to real robotic platforms. We really need to be able to detect this catastrophic forgetting. In our case, we've explored some very simple research strategies, but there's probably a lot more research that needs to be done in this direction and a lot more sophisticated approaches that should be developed. So this really is my last slide. Thank you very much for your attention. And these are like the papers I covered today, but more importantly, I would like to take this opportunity to thank my great collaborators for these different projects that I covered today. And yeah, like I'm very lucky to be working with them. Thank you very much. And I would be happy to answer any question on any part of the presentation.
Thank you. Go ahead for questions. Go ahead,
Very nice talk. How can you pretend to continuously learn with a model whose capacity is limited? I mean, I forget every time. That's normal. My brain is limited.
So, okay, obviously that's a great point. There's so much you can learn with a model, right? And we could discuss what is the most reasonable way to approach this. Should we have one universal model that is going to fit every single task? And I guess the question argues that we shouldn't do that, and I fully agree. But even with specialized models, I think it's important for model to be able to get updated from time to time, because even a known concept, its appearance can drift, or there can be new concepts that are related that should be handled by the model. So although it's impossible to be able to acquire all possible knowledge in one single model, there should be some plasticity in the model to make room for these new concepts. And there's always a trade-off between the plasticity of welcoming new concepts and the rigidity of not forgetting what the model has learned. And there's a trade-off to find. But there are techniques that should accommodate for both in a satisfactory manner. And this is really the kind of question we're looking at in this line of research. I don't know, I could go on for a while, right? Because it's very important. Maybe at some point your model should detect that it should be split into multiple models or some parts to specialize. But this is really going into very exciting but a lot more challenging research questions on model design. Does it answer the question?
Yes. Okay.
So thank you for your talk. Do you think that the recent trend of stable diffusion could help in the transferability for domain or for task, as in the pipeline?
So that's again a great question that is really challenging. I'm not sure I'll have a very definitive answer there. These models are absolutely amazing. It's fascinating how much they've learned and how much they're able to generate something. So they go into this line of work where multimodality is really helping for learning models that acquire lots of complex knowledge. I'm not sure I fully understand what's going on there and how powerful they are yet to be able to see how they could help with a continuous learning pipeline. But these, I don't know, sometimes called foundation models that have been trained on a very large amount of data, they should be, I guess, studied as a building block to build on top. So they partially solve the question on how should we pre-train, but there's always the question, how should you adapt? How should you specialize maybe for the target task?
Thank you for the talk. In the paper where you synthesize R negatives, I never dig into negative mixing, but since you want like a very general representation, it's kind of hard to define what is really a negative. And I wanted to know if there is any control on if what you are generating could be treated as negative, or if you just like take two negatives, mix them together and consider them as negative, if that makes sense.
Very good point. So let me maybe, there are two parts to my answer. The first one is, I'm going to claim that no matter what you mix, you're going to have a negative. Because if you're not, so for the proxy task, you want to recognize if it's the exact same image or not. So let's go back to our cat image, and you're mixing two other images. So it's very unlikely that by mixing two other features that are coming from two other images, even of a cat, then you create something that resembles so much your starting image that it looks like a transformed version of your starting image. So any mixed features is a negative because it is not directly a transformed version of your query image. And it is a very challenging task, instance discrimination, and this is why it generalized so well, I think. Now, I guess what is behind your question is that should we really treat the category, should we really ignore the category there? If we treat another cat image as a negative for the first cat image, is that an issue or not? And first of all, I think it's not an issue. And we did verify that. We had an oracle where when we started mixing things, we forbid the model to mix something that was from the same category. So if you were using hard negatives for a cat image, we would not allow to mix other cats. And this made like virtually no difference in the experimental results. So working with this proxy task is still training a model that is really appropriate for what you do, and is learning to discriminate between instances, images, and if what you want to do later is to learn the cat class and recognize cats, then this can be acquired afterwards during the transfer. But for pre-training, it's good enough what we do.
Thank you very much.
Some other question?
So about the contrastive learning, so you create another feature which doesn't exist in a sense. It's a mixing of two other features, but then you learn so that the distance of these new features gets away, doesn't get bigger. But then when you derive the math, it accounts to push the other features away. You know? I mean, you push the barycenter, so you can do this by pushing the two negatives you picked.
So I'm not sure I understand what is pushed away, the other negatives, I guess you mean?
So for instance, you create y, which is the barycenter of x1 and x2, and you say, then I would like y to be pushed away. But then the answer is to push away x1 and x2.
But these negatives are also in the batch, right? So we have a batch of samples because of course we cannot deal with all the samples at the same time. And then part of the loss is going to focus on a given pair. And we want this distance between the two representations coming from the same image, so this positive pair, to be smaller than the distance with everything else. But the everything else is both real negatives and synthetic negatives. The real negatives, they still exist, but we add more negatives that are, I would argue, even more challenging, because really we want to learn an invariance to this data transformation, data augmentation that are applied in the image space. But because doing transformation in the image space is super costly, we show that we can make this constraint stronger by also doing a mixing in the feature space. I'm not sure I answered the question. I don't know.
I would say that the distance of the synthetic feature is a function of the distances of the two of the features, the two negative features you picked. So if you want to increase the distance, you increase the distance of the two negatives. It's the same thing, the same goal.
But both are happening at the same time, and I'm trying to understand why this is an issue.
Oh, okay.
Maybe to complement on this question, did you try, instead of doing linear interpolation in the feature domain, to apply transforms on the image, like the transforms you apply on the positive, apply the transforms on the negatives instead, and then go to the feature domain? Maybe mixing negatives that are already transformed together before going to the feature domain, instead of this linear interpolation idea.
So this is something that had been explored already when we started working on the project, and this is a fairly standard thing to do, like doing the mixing directly in the image space, where you can apply pixel transformation. You can start like combining two images by gluing part of one on top of the other, or interpolating, and this works pretty well. But this means that you still need to extract a feature of these new images. So you're increasing your data set size. And this means it's a lot more costly because building this information is non-trivial. And then you still need to do a bunch of forward paths for all these images you just generated. And our goal was to show that we could do something by directly working on the feature space, so we don't need to re-extract features. They're out there, they're available, and we build on top of them. So that's really the mixing in the image space makes sense and totally works. But what we are working towards is something that is efficient, more efficient than doing transformation in the image space.
Okay.
Any more questions? Fedran, Pascal, Yanis, maybe?
No, thanks.
Yanis, hello, we cannot hear you. On n'a plus les sous-titres.
I can't hear Yanis. I don't know.
Yeah, okay.
Are you asking a question?
We cannot hear Yanis.
There is a shot.
Yeah, maybe you can write the question down, right?
Then we try the chat area to see if Yanis can answer this question. I hope you can make your keyboard work. Go ahead, Yanis. Again, it's going to be hard for the next work because you learn super good models, you have continuous learning. What's left? It's going to be tough.
Oh, there are so many things that are not solved, but they're fascinating problems, right? With so many open questions. Have you tried using diffusion models for some of your projects?
Not really for project, but
Huh?
yeah, we played it, we just played. But actually, yeah, generating negatives with diffusion model could be helpful. I saw a paper where they use a generative model for vision because we use it for text a lot because it's easy to generate text. Sorry. But yeah, it's starting to go with images, and there is some nice results. There was a paper at the CML where they used that to add information into the inference part. Like they make the model dream about the text, and so it gave like a visual clue about the input. So it's kind of nice.
Actually, I have a question. So I'm not sure I fully understood, but I think it's linked to the question of Teddy. So you have this positive pair, and they have a certain distance in the feature space, and then you have pairs that you can make between this anchor and let's say this positive and negative. Sorry, and then so the loss would be the delta between the distance between the positive pair and the distance between the negative pair, and you want this to be, I guess you want this to be negative. I mean, you want the distance between the negative pair and the positive pair to be, you want this difference to be positive. But so, could you just take, instead of taking a big batch, could you just take, instead of taking a big batch, could you just take the negative examples that's sort of, or the closest? It's like taking a smaller batch, but just taking the examples that are the closest, because then it's like your batch is not an average, but it's like you take the max of the mean, of the distance between the, I don't know if I'm clear, but I mean, for example, when you mix, can you just take, instead of taking I don't know how you choose the mix, but do you choose the mix to have the higher, the closest, to be as close as possible to the anchor?
So I think I got most of the question, but there are two parts, right? Like how we write the loss itself. And then we used one of the ranking losses, and there are many ranking losses out there, and they are all great and they have different properties. Some are based on contrastive, some are based on the triplet loss, some go for an average, some go for the max. So you have many formulations, and we have not like tried all of them, but we managed to have a contrastive based one that kind of worked well for what we wanted to do. So that's the one thing. And I think there's another part in your question, which is how do we choose the negatives that we decide to mix? And they are indeed some of the hardest. So there are some of the images that are the closest to our query. And maybe we shouldn't be that close, so they're considered hard. We know they incur loss, which is not the case of most negative in the batch, but those they are valuable because they provide information for training, because they are still very similar to the query, although they are negative, so they shouldn't be. And we synthesize by combining those, because we create some that are even harder, or at least in the problematic part of the space for training. And those are the ones we push away. Or they're still, I don't know. You look very puzzled, so maybe there's part of the question I still don't get. Yeah. I'm so sorry. I'm so sorry.
No, yes, you answered the question, but then I have other questions. Because, okay, so then, because you're doing interpolation, so how do you choose the alpha k? Like, is it a random number, or you try to be as close as possible to the query?
Oh, we tried many alphas, and I'm not sure 100% what is actually implemented, but I think it's multiple values. No, I don't know. Maybe we came with something that that we validated. I don't remember that parameter to be super crucial. The value of the alpha. Maybe we use a full distribution. Yeah, sorry, I would have to double check.
Oh, okay.
Diane, we have in the chat one question from Yanis. Can you see that?
Yes. Do you want me to read it out loud? So Yanis has a general question on self-supervised representation learning. And he rightfully says that there's a trend to evaluate this self-supervised representation by doing a full fine-tuning of the model on the entire ImageNet. And this really reduces pre-training to network initialization, with the argument that fine-tuning can be fast. But then all methods can only differ by 1–2% accuracy. So I tend to strongly agree on that statement. And personally, I think that if you train a visual representation for a task and you want to evaluate if your representation is good for that task, you should make it as difficult as possible for the visual representation. So maybe if you're deploying a full system and you can afford to fine-tune, you fine-tune. But if you study what your visual representation can do, then you shouldn't fine-tune, because you're kind of cheating. You're allowed to update your weights in your early layer. Some people even use heavy data augmentation. So then all the differences between the approach, they kind of like narrow down. And if you really want to compare what a visual representation should do, in my opinion, you should use it as a black box extractor, have your features, and build something on top super simple. Linear classifier, even k-nearest neighbors, so you're not even allowed to do anything fancy, and then you compare. Of course, you have lower numbers, but you can see what your model does as a pure feature extractor, without data augmentation, without anything else, without like maybe this method has better tune this hyperparameter for whatever, like simple, compare things in a very simple approach. And for this COG benchmark that I presented, we argue for this simple linear fine-tuning on top. And I know it's really not the standard way to do it in the community, but we have the full study with k-nearest neighbors as well that we've put in the supplementary, because we also believe that, there's no cheating with the KNN classifier. Anyway, that's, but it's true. This is not the way representation are typically evaluated. So I don't know. I'm told it's totally fine if, in this room you disagree.
Thank you. Any more questions in the room here? So we have to thank you very much, Diane, for this very, very clear and excellent talk.
Thanks a lot for the great question, the discussion. I wish I could be, we would have discussed longer about your take on what a good representation is, and yeah. So thank you very much for at least allowing me to attend virtually your meeting.
Thank you.
Thank you.
Thank you very much.